So, hi everyone, this is problem number, I'm not even sure. I skipped like three problems in between because they were vector calculus related, and vector calc doesn't show up much in Olympiads. And to be honest, I hate vector calculus, so I didn't want to do them. They're very math heavy. Now we want the part B of this, which is a little bit trickier, and I'm gonna honestly struggle solving this on here because I never originally solved this question and I just looked at it. So if my explanation is a bit wobbly and I'm like thinking to myself a bit, just forgive me for that. So what this second part is for an overall neutral charge distribution within a sphere of radius r. Let me just draw a sphere. That is not a sphere of radius r. That is also not a sphere of radius r. Please, come on. Yes. Okay, sphere of radius r. The average electrical field over the interior of the sphere is minus p, this is vector quantity, over 4 pi epsilon naught r cubed, which is the total, where p is the total dipole moment of the charge distribution. This is interesting. So we have sort of a dipole moment here. So I think we should define our dipole moment, right? Usually with a dipole moment, what it is if you have a positive charge here and negative charge here, and there's like a vector, oh sorry, that should be negative. Um, so a negative charge here, positive charge here. And there's a vector pointing from the negative charge to the positive charge of like, let's call it r vector. Then the dipole moment is defined as like, and these both are q, is defined as just q times the r vector, right? Now, this definition isn't going to be used in the question. We're going to sort of generalize it because we have like a general neutral charge distribution in the whole sphere. So that means we'll be working in terms of like some sort of charge density rho. So we want to find an expression for a dipole moment in terms of this rho. How we find that is we can do the integral over the charge distribution of the r vector times dq instead of just q. So we integrate over some dq over the whole charge distribution. Now this dq for any point is going to be simply rho times the volume element. I'm using the symbol for volume element. So our dipole moment is going to be an r vector times the density at a certain point over times the volume element, all integrated together. So that's, and you're going to see that later on in the proof, this quantity should pop out. Now, how do we actually tackle this question? I'll give you a hint. It's going to be tackled using the same Newton's third law trick from the first part. Let me just erase a few things around here. Actually, I'll erase all this and just highlight this, I suppose. I hope that doesn't ruin it. Okay, there we go. Is we're going to use the same Newton's third law trick here. Now we have some, in this sphere, we're going to place some arbitrary weird charge distribution. And that, in what we want is an electric field over the whole interior of the field, whole interior of the sphere of that charge distribution. Now from the previous part, we knew that to sort of gauge out what the average E field is, we wanted to look at how the point particle that we were using, what type of electric field is going to exert. And for that it was very helpful to think about just placing a charge q over the surface of the sphere, because then our electric field has something to actually act on, which meant that we could use the force formula QE average, because now there's actually some q to multiply by the E average to get the force, and then the E's cancelled. So we can do sort of the same sort of thing. So we want the electric field to actually be applied on something. So in this sphere, why not make a spherical charge distribution of where this total charge Q uniformly distributed in the interior of the sphere. So our sort of our like sphere, the shell we're working in, we just place a uniform charge distribution inside of it of capital Q. This is sort of a fictional charge distribution. It doesn't actually exist in the problem setup, but it'll be very convenient because it'll let us use the same force formula that we used before. I've used this symbol sigma for the charge density of the imaginary charge capital Q that we've sort of fictionally created in our sphere capital Q, uniformly distributed, and I've just named this sigma with a different symbol to differentiate it from this rho over here, but it's the same thing. Now what we're going to do with the question is we introduce this big Q charge just so we could look at the actual force and this equation F equals Q E average. So let's look at it. Right now there's two charge distributions in play here. There's our uniform charge distribution capital Q, and there's the random charge distribution small q. The force exerted by Newton's third law, the force exerted by the small charge distribution on the big charge distribution is the negative of the force exerted by our uniform field capital Q on our our random neutral field small q. So, and this will obviously equal to big Q times E average. And this is what we're going to use to solve our question. The thing is, we can actually find this force pretty easily. The force our uniform charge distribution of Q will exert on this neutral charge distribution. How do we find it? Okay, we have the sphere here. This is the center of the sphere. Consider some random volume element d small q of our neutral charge distribution a distance of small r away. And let's try and find the electric field, or sorry, the force on this charge element. Now we can construct a Gaussian surface, which is just a small spherical shell of radius r. And this will contain a certain charge inside of it of the uniform charge capital Q, and through that we can find the electric field here and thus the force. The electric field will point outwards here. So we have a distance r, we have a charge d small q over here, and we want to find the force on the charge due to the uniform field. We've constructed a Gaussian surface inside of here, and this Gaussian surface will have volume 4/3 pi small r cube, while the whole sphere has volume 4/3 pi capital R cube. Using Gauss's law, the electric field times 4 pi small r squared equals the total charge. Now the total charge will be this charge density sigma multiplied by the volume inside here, right? So it'll just be Q over 4/3 pi capital R cube times 4/3 pi small r cubed, and this will be over epsilon naught. The 4/3 cancel, the pi cancel, and we get E is equals to Q r over r cubed times epsilon naught, 4 pi r cubed times epsilon naught. The way we get that is this r squared divides on both sides, this 4 pi divides on both sides, and this is the result we get. In terms of vectors, we can write it as Q over, let's replace 4 pi epsilon naught with K, the constant K, because that's just easier to read, divided by capital R cube times this R vector, which is the vector pointing radially outwards. Oh my god, my screen shifted. The vector pointing radially outwards is R, the vector R. So we found an expression for this electric field on this element of our neutral charge, and we know the force is just Q times some electric field, right? In this case it's a dq, so our force is E d, oh my god, dq. Writing this in terms of this volume element that we have, instead of in terms of just dq, let's write in terms of densities and volumes. We get, and let's make this a vector. We get um time the our E vector times rho, the density from way earlier for a dipole moment expression, times a volume element. So, and this is some small force on a small volume element. That'll mean that the total force exerted by the uniform charge distribution of capital Q on a non-uniform one is going to be the integral of this, which is E vector times rho times d tau or whatever it's called. Now, this electric field we found over here, and we can just plug that in, so it'll be k, so that's a way bad handwriting, k capital Q on the outside divided by r cubed, and inside we get rho times our r vector times our volume element. Notice something very interesting. This same this same expression, r vector times rho times the volume element, is our dipole moment. So that means that this force, which is the force of the uniform charge distribution, I'll write this in blue. The force of our uniform charge distribution on our random one that already existed, this is the imaginary charge distribution exerting a force on the one that was inside the sphere that we're looking at. We'll replace this all by the sort of the dipole moment, so it'll be k times the dipole moment of the charge distribution times capital Q all over r cubed. Now, from this relation we had earlier, oh my god, from this relationship we had earlier, we want this force. We don't want the force of the uniform charge distribution on the small charge distribution. We want this force here. So to do that, we just add a minus sign. So the force of our charge distribution on some random uniform charge distribution that we imaginarily place in the sphere would be minus k times the dipole moment times capital Q over r cubed. And then this all equals to capital Q times E average, and dividing out you get that E average equals to minus k times the dipole moment all over r cubed. And that's a wrap on the question. I can't speak. I'm sorry. I'm horrible at speaking. But yeah, thanks so much for watching. This was, I'm pretty sure, problem number 7. Now I'll record problem number 8 and upload it. Thank you so much for watching, and yeah, thanks.